All right, we're recording it? Yeah, we are, aren't we? I can see a icon. Okay, cool. So, welcome to, this is the third seminar, isn't it? Welcome to seminar 3 on the Kitaev model. I'm Alex presenting. That's the disembodied hand. And yeah, this week we're actually going to introduce the Kitaev model, and yeah, hopefully, time permitting, we're a bit short on time today. Like, use Majorana transformations to at least express it as a quadratic form. So, first of all, what's the model? And the answer to that is we're modeling a spin system. So, on a honeycomb lattice. So I'm drawing out a nice little honeycomb lattice here. And let's go over these sites, I, J, K, at a K, etc. And at each one of these, we have like some particle which could be spin up or spin down. So like a hexagonal lattice. Yeah, as will be revealed in this talk, my background is more in like analysis than in like physics. So there's gonna probably be a few times where I pause and say, hey, physicists, why do we do this? Like, I imagine that this would be sort of like, well, modeling some kind of magnet that is like, has a honeycomb crystal structure. But anyway,
that's absolutely the case, by the way.
Cool. Yeah, I want to note that there's 3 directions in which these lines can go in, which I'm going to label X, Y, Z. So on my little drawing, here's the X's, here's the Y's, and here's the Z's. So those directions are important. Like in the model, each one of those has a different weighting to the spin coupling. So the Hamiltonian is written as is there a minus sign? There is. Why did I do sigma y? So we've got the terms where like it's the sum of ij with an x link. So the pairs of spins that have a link between them in the x direction, and then a set of ij's that have a y link times a set of pairs linked in the y direction. That should be sigma j x. And lastly, there's the z direction. So we have different coupling of like different strengths of spin coupling in like each of these 3 directions. Now, a slick bit of notation, a slick bit of notation we introduce is we would write like sigma I superscript alpha ij, this times this, where alpha ij is either like x, y, or z, depending on the direction of the ij length. So then we have this if we have an x link, y link, and a z link. So we can then write this in terms of this. Like each term of this is then going to be j alpha ij, where alpha ij is again whichever direction we need times that. And we can call the sigma ij, the sigma I, sigma j, in the matching directions. Kij, which lets us rewrite the Hamiltonian like this. Kitaev does this later, like after we've, like when we're rewriting it as a Marijuana system, but I figured I might as well do it now. And yeah, also, before we move on, I'd also just like to quickly mention that sigma I alpha generate a Su2 Rim. So if you're ever lost, then we have these, like you can just know they multiply together to I and they anti-commute. Yeah. I'm going to write this in this form. So this also tells you that they square to the identity. So really, if you just knew that they squared to the identity and you had this one, you could figure out anything you needed. Yeah, in my notes, like I did pretty much all the commutators by hand. Well, again, because this is not something I'm 100% familiar with. So it's like, if it's confusing, just go through the details yourself. Like it makes it make sense. So yeah. Now, that out of the way before.
I guess something that wasn't totally obvious to me, right, was I'm used to Su2 reps imposing a commutator algebra, but this, I don't know, it seems to me that this anti-commutator algebra is heavily reliant on choosing specifically the Pauli representation of Su2.
You should be able to show just in the like universal enveloping algebra that you have this anti-commutator relation. Like, well, just by isomorphism to like the Pauli matrices. But I think that I kind of like thinking of this as just a slick way to go about it. But you are kind of right. We do, like in the calculations, I found a lot easier to use like this form of it instead of just going back to the Lie algebra or going back to just using commutators. Yeah, that's interesting. Anyway, is what I just said even right? That the anti-commutator relationship holds in Lie? Maybe not.
And at any rate, I guess it doesn't really matter because I mean it's sufficient to know that like there's a representation which this holds, and then you just like build the model exploiting this fact. Like yeah.
Quickly, I need to plug something in. Namely my tablet. Yeah.
No, sorry, actually, it's actually quite kind of natural that this sort of doesn't necessarily play nice with the Su2 structure, because in some sense the Kitaev model breaks Su2 symmetry. Well, sorry, to qualify that a bit, like there is still an Su2 symmetry in the model, but it's no longer the full Su2 symmetry of having that many independent spins.
Right.
Yeah. Anyway, we'll think about it for next time.
On the topic of symmetries of a Kitaev model. Yeah, it's a good enough segue. I'm going to introduce the like flux for any given plan cat, which in this case are just hexagons. So I'm going to label the vertices of it. Oh yeah. You're probably going to not need the odd and even letters today. But yeah, I'm going to write down like the flux for a pancat is what you get when you take these link operators going around the perimeter of one of these hexagons. And yeah, you can write this out in full with sigma. Well, in this case, it starts with sigma zi, sigma z2, and so on and so forth. And you can use the defining relations of SU2 and obtain just that this is equal to the normal direction at each point. So, well, normal is a bad word considering it's at the corners, the outward direction. So, sigma. Oh, here, I've mislabeled this. Have I mislabeled this? No. Okay, this is meant to be x. Yeah, that is x. Cool. So it's sigma 1 x, sigma 2 y, sigma 3 z, sigma 4 z, sigma 5 z. What am I doing? Sigma 4 x, sigma 5 y, sigma 6 z. So just cleaning things up a little bit. Now, another like what I'm going to note is that this actually, you can show that this commutes with all the kij's. This breaks down into a few cases. Like you just consider either a length that's isolated from the hexagons, which is pretty easy. Well, from the hexagon blanket, I mean, or the case where you're touching it, or the case where you're it's one of the edges of the hexagon. And yeah, cases are listed in increasing difficulty, but none of them are that hard. So these things all commute with the Kij, which means these commute with the Hamiltonian. Because the Hamiltonian is defined, well, can be defined in terms of the Kij's. So, yeah, that's neat. And another thing about them is they commute with each other, which there's two cases to consider, which is adjacent hexagons or non-adjacent hexagons. And non-adjacent hexagons, everything in sight just commutes. Oh, something I want to note. These spins on different sites commute, which is very important. And it's not the case with annihilation operators, which is something which is, yeah, I was a bit of a novice physicist that making sure I appreciated that was something that tripped me up a little bit. Anyway, so these commute with each other if you pick two distinct hexagons or planchets. Two. So I want to note that this form makes it quite obvious that the square of these operators is the identity. So with all these three facts, we have one, well, also, yeah, we have these things are simultaneously diagonalizable because they commute, and their eigenvalues are plus or minus 1. So, like, we can come up with a basis of L of eigenvectors, of simultaneous eigenvectors for all WP.
Just to be clear, the L is the Hilbert space, right?
Yeah, sorry. L is the Hilbert space of states, which we're considering a spin model, so it's like two-dimensional space. Like at each site, we have a two-dimensional like Flux space generated by up and down, and then we take a tensor product of n of those for each one for each side. So it's dim 2 to the n. Thanks for that, Alaric. So simultaneous eigenvectors. And so given that we have, like, we can write everything as some, like, in terms of like vectors which are like eigenvectors for each one of these planchets. Or so let's decompose this into like which sign we've chosen. So what I mean here is like W, like say, like L W1 all the way up to Wn means like the subspace of L where like W1, like for say like when we've numbered our planchets somehow, acts on this space as Wi times the identity. Well, W1 times the identity, because I said W1, but each one of these acts as an eigenvalue on these. So now we're doing this now before we Majoranize stuff, because this decomposition is it turns out that you can come up with a version of this decomposition after you've Majoranized too, which is quite neat. And so essentially, it's going to boil down to solving the problem that we'll be able to explicitly solve when we get to it is like the problem on just a Majoranized version of one of these. Well, that's the problem which is going to reduce to like a where the Hamiltonian is going to reduce to some quadratic form.
Just a comment about like why the Majoranas are even necessary, because it kind of seems like we've solved everything here, right? But I don't know.
Yeah, Alaric has a good point. Just like, why do we have to Majoranize stuff? Like, this is a lovely looking decomposition. The problem is, well, like these things are potentially quite big, right? Like, is that what you want to say? Just
yeah, I guess just that like we have sort of rendered it block diagonal, but each of those, but like LW1 to WM, like there aren't enough dimensions available from like W1 to WM equals plus or minus 1 to span the entire Hilbert space. So yeah, like each plaquette has got 6 spins on it, and each spin belongs to only 3 plaquettes. So there are exactly half as many plaquettes as there are spins. So like, yeah, so that means that the dimension of each one of those little LW1 to WMs is going to be, each one of those is going to be 4D.
No, they're going to be 2 to the n on 2 approximately, where n is the number of vertices. Like, this is a heuristic argument used. Like, if they were 4D, I feel like that would be quite solvable, but they're they're 2 to the n on 2, which like, this is like TCMP, so n's going to get big.
Wait, no, but like we're in eigenstate of like a simultaneous eigenstate of all of the plaquette operators. Oh wait, hang on.
Yeah, there's one of these for each. There's 2 to the m choices of
you're right.
WM words. So that's what this denominator is here. And then there's 2 to the n vectors. Oh man, I even wrote that on the same page. So the dimension of each one, like assuming that we there's not many boundary terms and that, yeah, assuming that there's not many planchets on the boundary,
Or
and
or
that,
or just chuck it on a torus and it becomes exact.
yeah, sure. Yeah. Yeah, modular a few error terms, like we can just approximate, well, and assuming that all these have about the same dimension, we can approximate the dimension of each one as 2 to the n on 2. So yeah, on average, these things have like quite a high dimension, and then like trying to diagonalize the Hamiltonian in each of those seems not like something you can solve exactly. So, and this was famously an exactly solvable model. So we need to Majoranize. And wow. First of all, I'm going to note that if we have a system of K fermions, well, fermionic modes, let's say, this is modeled by having annihilation and creation operators for K equals 1 all the way up to n, and these have to, well, yeah, and these are fermionic operators, so these anti-commute. At different sites. And also, if you pick 2 of the same one, the commutator is 1 equal to 1 times the identity, which, yeah, I won't talk about it because it doesn't, being just 1 times the identity feels a little unnatural to me, but it's fine because like we can come up with a basis which doesn't have that efficiency. So we're going to come up with CI operators for I equals 1 up to 2n. So C2k is AK plus AK dagger, and C2k minus 1 is 1 on I, AK take AK dagger. So these one, you can actually write the commutation relation for these really elegantly. Well, the anti-commutation relation. So this is just 2 times delta ij. So think of it as an exercise. You pretty much just pick the K distinct or K just indistinct cases, and it comes out in the wash. But this, yeah, this feels to me more natural because this is the, like, this is what you do when you're trying to write the algebra, well, the generators of a Clifford algebra.
Yeah, a thought that I just had is that the one might feel more normalized because then in your definitions of your Majorana operators, they are in some sense normalized.
Yeah.
But same really.
Yeah, you could just could you just rescale stuff? Probably.
Yeah, I think
Absolutely.
Yeah.
I'm even gonna note signature. I can't remember which sign convention used, but it's the one where everything's squaring to 1. So yeah, it's also a complex Clifford algebra, so it doesn't really matter what the signature is up for isomorphism classes. Yeah, so now what we want to, like, for a single spin, how we model this with Majoranas is we're going to say we have a 4-dimensional Fock space. So we have 2 fermionic modes. So we've got A1, A2, A1, A1 dagger, A2, A2 dagger. And we're going to get from this 4 Majorana modes. And what we're going to do is we're going to label these C, B1, or C, BX, BY, and BZ. And now, here's where I'm going to use some slight shorthand notation. Is the C first or second? Let me check my notes.
I think it's second.
Cool.
I love
matters.
fermions.
Yeah, and look at these. We've you can show, well, you can show that parts of the defining operations for these work. So we can write that these square the identity, but they don't actually satisfy the other constraint we need. So if we calculate this, then this actually equals I times some operator I'm calling D, which is bx, by, bz, c. So if you recall our like the defining properties of the Pauli matrices are that if you multiply them all together in a with the right sign of permutation, you get I, and they square to the identity. So here we don't quite do that, except you can note that D squared is equal to the identity. So what we can do is we can decompose, we can look at the subspace I'm going to put a hat on this retroactively, of this where D equals the identity. Right? Because D squared equals 1, so D has eigenvalues plus and minus 1. Oh yeah, something Kitaev kind of asserts but didn't prove was that M is two-dimensional here. I think this should be true because I think that this is true because you can use any one of these Majorana operators to interchange the plus or minus eigenvalues, eigenspaces. This is in my notes, but yeah, you can do a little bit of this. Put the C over there, get a minus sign, and you get minus C d phi. And then, so yeah, doing that means that you can use C to interchange plus or minus eigenvalues of D, and this shows that they're isomorphic. Now anyway, so that's how we can do one spin, and we've proved by the definition of D or of M no hat, the Pauli matrices, or these sigma tilde operators give a SU2 representation. So on here we have an SU2 representation, and yeah, we can realize our spin system as we can Majorana as a spin system by doing this at every site. So instead of going from some Hamiltonian in spins, we go to some Hamiltonian in the Majoranas. And we just define this by just like taking our old Majorana in terms of the spins and like inputting sigma alpha instead. Right. And yeah, when we restrict this onto, so to recapture the original system, we need to look at the space where each single one of these spins satisfies the Pauli relations, which means that we have to, like, each one of the DIs has to be acting as the identity. So Li is going to be I'm going to write it in a somewhat convoluted way. So this is like our system is 2 to the 2n dimensional. Why did I do it? Anyway, we want on each I, we want di equal identity. So we write L equals I'm going to write this as the intersection of I equals 1 to L of the kernel of di minus 1. Right. So, and then H tilde of bi alpha ci restricted to L is just H of sigma I alpha. And I just have time to write what this thing equals. So, sigma I.
Hey, Sav, could you flash the last slide again?
Cool.
Equal Dunker.
Yeah, the Hamiltonian just restricts down to, like, on this, well, we call the unhatted space the space of physical states. And L tilde of extended states. So, yeah, just gonna, the last thing I'm gonna do before we have to head off is I'm gonna just write down like how we can rewrite our Hamiltonian in terms of Majoranas. J, so we already had this form, J alpha ij. So this is then becomes I bi alpha ij c I bj alpha ij c j. And we're going to group this somewhat interestingly. So I'm going to write this as minus I times I bj alpha ij bj alpha ij ci cj.
Sorry, isn't there another I on the second spin?
Another I?
As in, like,
Sorry.
each of the sigma squiggles have got an I on them.
Sorry, this is sigma I superscripted with alpha ij. It's meant
Oh,
to be, right?
no, I mean, as in another factor of square root minus 1.
Oh, yeah, I see what you mean. Cool. Yeah, sorry, I did forget that. Also, write down the thing I'm actually calculating. So what we're going to want to do is to make this look like a quadratic form. So we're going to want to just sum over all possible pairs instead of just the ones that are linked. I've been omitting that, but that's the only terms in the sum. So I'm going to define an operator, which is going to be the coefficients. So, oh, there's also I dropped my mind. Should I have them?
Another minus sign cancels with the factor of I squared.
Yeah, okay, cool. Oh, right, yeah.
By the way, the
Yeah.
overall sign of these J's doesn't actually matter for the spectrum, so they're sort of free.
Yeah, but I do want to write this as we should be careful about signs. So yeah, but should be, oh right, so that minus sign cancels and I end up with, I'm gonna write this with the following sign convention. So summing ij, a hat, ij, ci, cj. So you'll notice that's a factor of 4. Factor of 2 you could excuse because here I'm unrestricting I and j, so I'm going to double count each pair. But a hat ij is defined as I, bj, alpha, bi, I swapped the order of these accidentally. Bj alpha ij, bj alpha ij times j alpha ij. And I'm putting an extra factor of 2 in there to explain why we're dividing by 4 here. For I and j connected. And it's 0 otherwise. So yeah, I think I should stop there. But we've written this as, yeah, like with aij is then going to be anti-Hermitian. Aij is because these like bi and bj anti-commute. And but we also have a factor of I at the front. So with that definition, we have something which kind of looks like an a skew symmetric quadratic form operating on the CIs. All right, that's what I said I'd do, and I'm gonna stop there. But yeah, stop if you